Okay, so hopefully we'll be able to have a live stream now of this, and I can post this right to the website, and you can read it. That's the new goal here. We'll see how it goes. So far, my live streams at the other school have not worked out so well, so we'll give this a shot. Okay, so we have covered these before, but you know, it's good to review these now that we have a little bit more information. So that's what we're going to do right now. So we talked about two different situations in the human body. There's the situation where someone takes food in, or gets an increase in glucose, and there's also a situation where the individual is low on glucose later in the day, and they need some sugar to balance the body out. So the first situation is what we call hyperglycemia, and that's when someone has increased the amount of sucrose in their body, or glucose, any sugars in their body, and so the body has more sugar than it's used to. So you already have this written down. I'm just going to add this in here. So this will be the hyperglycemia root. And so the situation here is that we get an increase in blood sugar. So this could be from eating some candy, or from having something, even just eating some food. We saw yesterday that the amount of carbohydrates in something like a piece of sweet potato, right? The sweet potatoes tested very high for carbohydrates yesterday. So even having some sweet potato, you're going to increase your blood sugar count. So we can just put a cause here. Any cause that involves getting your blood sugar up. So eating in general, eating some let's just go carbohydrates. I'll be even more general. Sorry. Okay, so we eat some carbohydrates. Those carbohydrates start to get dissolved by some enzymes. What's the first enzyme that hits those carbohydrates in your mouth? Salivary amylase. Very good. So salivary amylase breaks those carbohydrates down into some of their disaccharide forms, and then those disaccharide forms are going to be broken down even further as they enter the small intestine and the stomach, and they're going to be broken down into their monosaccharide forms, their glucose, their fructose, their fructose. Is there another one? Maltose? No. Sorry? Yeah. Oh, there it is. Galactose, there it is, yeah. Galactose. So salivary amylase, it breaks down into the maltose, the sucrose, the lactose, and then that maltose breaks down into two glucoses. The sucrose breaks down into the glucose and the fructose, et cetera, et cetera. So we eat some carbohydrates. We can put that, maybe let's put that as a little thought bubble here. I always make my thought bubbles too small. So the starches So starches break down into disaccharides by salivary amylase, then into monosaccharides by the other enzymes, and that's your glucose, fructose, and galactose. I always like galactose because it sounds like galaxy or galactic. And so, and those are easily absorbed into the blood. Which absorb into blood and small intestine. Alright, all done. This is my little thought bubble here. So we eat some carbohydrates. If they're starches, then they get broken down into disaccharides by salivary amylase, and then into the monosaccharides by their other enzymes. You have your maltase, your sucrase, your lactase. And then you'll be left with a bunch of the monosaccharides, or the simple sugars. Those simple sugars can be directly absorbed by the blood and transported around the body. Sucrose and glucose and those things can be absorbed into the cells and broken down to form ATP and other energy sources. But your body doesn't need that much, right? Your body needs a specific, a sort of standing level of sugar, a equilibrium level. And so we don't need to, we don't need all of that sugar that's going to be broken down right away. So if you have a very high carb meal, you eat a whole bunch of bread in the morning, or this morning I ate a bunch of sugar cereal, because sometimes in the morning I just need a little bit of cheer in my day, so I have like some chocolate, I don't know, it's like chocolate brownie marshmallow cereal, and you know, it's makes me feel like a little kid again. But there's a whole bunch of simple sugars in there, right? So I'm instantly getting a sugar rushing to my blood supply. So the blood sugar in this case is changing. So the change here is going to be that your blood sugar increases. And of course, the normal condition, this is an increase from your normal condition, which is regular blood sugar levels. You want me to convert this to text or is that readable? Sometimes it's not. There's an interesting set of studies that they're doing into how much of an effect on insulin the false sugars have, or the synthetic sugars, the artificial sugars. So things like sucralose and stevia and those other sugars. There is an interesting amount of work going in to figure out if, because they taste sweet, do they cause the brain to start this process of like releasing insulin, and if that's any damaging on the body. At this point, it's been pretty inconclusive. They've found that for the most part, artificial sugars are pretty stable and pretty, or have not really shown any great danger. But you know, that work is going to be continuing probably forever. They say, some people say that something like aspartame, which is the one in like Diet Coke, They say aspartame is like one of the most well-studied chemicals in the world. It has the most there's the most studies have been made on aspartame, but the majority of those studies were paid for by cola companies. So, but cola companies have a vested interest in keeping you alive, so you continue to buy their products. So, you know, maybe like, you know, depends how much you feel that's not a thing. You know. Anyways, I'm not sure where I want to go with that. Okay, so the receptor here is there are these glucoreceptors. They're that are throughout the body. I believe they're in your blood. So we're gonna call these. Or yeah, I'm gonna write it incorrectly. So okay, so glucoreceptors. And they will send control to the brain, specifically our old friend, the hypothalamus again. So we know there are glucoreceptors. Oh, Linda, how are you? Come on in.
Good. Is that test yesterday that I go to work?
We haven't done a test. We did a lab yesterday.
Oh.
Grab that though. No. You did a test a while ago, didn't you? Yeah, you did the test. You're good.
Oh.
Yeah, we have a test on Friday. Okay. Apparently the work is still out on where the glucoreceptors are, and it will not show me the rest because that website is locked. Okay, in 1990 they said that there were glucoreceptors in your brain, in the hypothalamus. Utilize it properly. That's kind of nice. The hypothalamus is a receptor and the control center. So the hypothalamus is then going to send a instructions to, and do you remember who the hypothalamus is sending instructions to? Who's going to respond to this high sugar level? What organ? Heard it, I think. Pancreas, yeah, that's the one. Very good. Okay, so this is the pancreas. And specifically the beta cells in the pancreas. So beta is a funny looking bee. Usually has a long tail. It's a Greek letter, not it's like the ancient Greek letter, not just a big B. Certainly a letter that B is based on, but that's a later Roman letter. So beta cells, and we also call these the islets. Oh boy. Let me rewrite that. Islets. This is an I. Anger. Bonds. So the islets of Langerhans, that's you know, pretty fancy name. if you are a famous enough person or you discover something new, you sometimes get to name them after yourself. We just often call them the pancreatic islets, but they are a section of the pancreas that contain some hormone-producing cells. They are named after the 1869 discovery by German pathological anatomist Paul Langerhans. So that's why they get to be called the islets of Langerhans. 1800s, you know, we still have some loose rules for naming things. You just name them after yourself. Or it'd be popularized by some prop somewhere. Yes, it's islets, so I-S-L-E-T-S. Let me just do a conversion on this, and then it'll help you out. This is a, I don't know how I'm going to do beta. I'll just leave a big space on it in there. Islets of Langerhans, yeah. So beta cells for hyperglycemia, beta cells are for when the blood sugar is high. We're going to see in the next one, when the blood sugar is low, it's the alpha cells that are important. So the result is that these beta cells release which hormone? Which one's released to reduce blood sugar content? Insulin, very good, yeah. So insulin is released. Allows cells to take in sugar. And for glucose, convert glucogen. So insulin is released, allows cells to take in sugar, and for glucose to convert to glucogen in the liver for storage. This reduces the amount of blood sugar. Now that sugar that was in the blood is either in a cell or in the liver, and the blood sugar is reduced back to normal levels. So this is something we've talked about before. We talked also about the two sort of digestion-related diseases, such as type 1 diabetes and type 2 diabetes, where we have factors that affect this cycle. So we have the type 1 diabetes. This is where this is the child onset diabetes, I believe. So it's where no insulin is produced, ineffective insulin production. And type 2 diabetes. This one is usually, there are some genetic factors, but also some lifestyle factors that are affected. So the type 1 is also known as the childhood onset diabetes. It's the one that you can have, that children can get. Type 2 would be the type that you might get when you're pregnant, or you might have as a factor you might develop later in life. Body can develop a resistance to insulin, and the cells no longer use it in the effective way.
What's the difference between 1 and 2?
Right. So type 1 is usually is a genetic disease that a child can be born with it. It's the body, these beta cells no longer produce insulin, so they just straight up stop producing. This one, in type 2, the insulin levels are reduced. So your body's not producing enough insulin, or your body's cells have developed an insulin resistance.
Is that like being obese or something?
Yeah, so these ones, these factor, for type 2, usually there's a genetic component in terms of like you have to have a predisposition for type 2. So if it's a type of diabetes that runs through your family, then you have a higher chance of developing it, but it's one that develops because of factors. The last I saw, there's sort of five factors that they kind of consider, and I've forgotten most of them. But they are one of them is genetics, another one is lifestyle, another one is nutrition, and whether you're taking in sort of a stable diet. Other factors like drugs and alcohol use would be another factor that could contribute, decrease the effectiveness of your cells. High calorie diets or high sugar diets are increase your chance as well. It's one of these things. We all enter life with a certain genetic lottery, and then from that genetic lottery, depending on what steps we take, we increase or decrease our chance. But everybody kind of starts with a certain base chance in different things, and those chances are different. So some people will start with a much higher risk of cancer, but if they never smoke or they never engage in those risk factors, then they might not ever develop cancer. But whereas another individual might have a very low genetic risk of cancer, but then they smoke all their lives and they do a whole bunch of other things. They have risky jobs and stuff, and then they increase it to the point where they develop the cancer. And also it's always a chance. So even if you have we have lots of people go to the lottery with 0.001% chance of winning, but at least somebody wins, right? So in this case, I guess it's a loss if you develop. So depending on your genetic factors, the chance of developing type 2 diabetes might be there in a significant chance that, depending on the lifestyle choices that happen after that or lifestyle events that happen, you could be at risk. Type 1 is typically one that once type 1 is one that's inherent. Like if you have child onset diabetes, you've got child onset diabetes. It's a factor you'll have to live with for the rest of your life. Your body's cells have this genetic inclination to not make insulin. There's something at the genetic level. There's something in the information in your cells that prevents insulin from being formed. So it's really sad, But I mean, it just kind of sucks because it's like it's your body. You don't get to choose that part, right? You don't get to choose what genetics you start with, and you just luck of the draw. And I mean, it's I have a friend whose kid developed type 1 diabetes. Only one son. It's never been like a factor anywhere else. It's just essentially a random mutation. Everybody carries about 3 random mutations, and that was his, and it was an unlucky one. So he now has a little box that he carries on his hip, and it's an auto injector. They're pretty expensive, but they essentially have a blood sugar tester that it's constantly testing your blood sugar, or it's testing it like every 15 minutes or half an hour or whatever. And then it has its own supply of insulin. And then whenever it detects the blood sugar levels are too high, it auto injects insulin into the individual. And it's very small. It's like it's held on his belt or something, and he doesn't have to worry about it. Prior to that, he of course had the classic sort of little box that you would take. You poke your fingers, you get a blood sample. Then if your insulin's high, then you had like a set of little needles that you could take insulin with. But usually it has to go straight into the blood. Insulin's not strong enough to go through the digestive system and wait to be absorbed. You want it faster than that. Most of the insulin we have today is created in the lab. It's manufactured by bacteria. We have genetically modified bacteria that produce all of the world's insulin. Prior to that, it was extracted from the pancreases of slaughtered animals. So that's also a cool part. Yeah.
What does pancreas do that works as an effector?
What does the pancreas do
That works as an effector?
as an effector? Well, because it's the one causing the change, right? So the pancreas is the one that has these beta cells.
So is it releasing the cells?
So those beta cells are hormone-producing cells. They produce insulin. So they're just essentially cells that their only job is to produce this specific chemical. And then when they're signaled by the hypothalamus, they secrete that chemical into the bloodstream.
What about those people who get a pancreas removed?
Right. Yeah. So they're probably going to be looking at some sort of like insulin injections for life. Yeah. Pancreas damage or pancreatic cancer, right? Essentially, is you're getting yourself a type 1 diabetes out of that, essentially, because you don't have a pancreas anymore. You're going to have to. Yeah. Pancreas is really, pretty essential piece of equipment. Okay, so the other case is the sort of end of the day. You haven't had anything to eat. So that is your hypoglycemia. So this is going to be hypoglycemia. You already have that written down. I'm just catching up. So in the hypoglycemia, almost the same organization. We're going to have our normal blood levels, normal blood sugar. Down here. And then the cause is usually going to be a lack of food. So you haven't eaten. So you don't have any food that's currently being digested, or the food that's being digested is not releasing monosaccharides. Maybe you're digesting some celery. Celery doesn't have very much sugar in it, so it's just mostly fiber. You're eating some celery or some pickles. Pickles are a negative calorie food, so that means they have very little carbohydrates in them. I don't know if they're negative calories. It's like negative 1 calorie. So popcorn has very little calories in it. So you spent the whole day eating pickles, popcorn, and celery. You don't have very much sugar. You didn't take very many carbohydrates in. You took in a lot of starch. You took in a lot of fiber, but you didn't take in much else. Maybe some water. So now your blood sugar levels are starting to drop. If you were trying to, if you do any bit of working out at this point, you're probably going to feel a little lightheaded because you don't have very much sugar in your blood supply right now. So blood sugar drops. While you're working out, you'd like to have some blood sugar because your muscle cells are going to be looking to take in more sugar from the blood supply to convert to energy as soon as they can. And so then the glucoreceptors, which we said were near the hypothalamus, or at least as far as we know, they're in the hypothalamus. Receptors. We're probably going to imagine that these are, what's sort of happening is that the blood, right, the blood is being pumped all around your body, and then some of that blood is being pumped all the way to your brain, pumping right past these glucoreceptors. And if the glucoreceptor detects that there is a lack of blood sugar, then it's going to send a signal to the hypothalamus, and the hypothalamus is then going to send a signal to the pancreas. So the hypothalamus is a part of the brain which handles a lot of these factors, and it's sending another signal to the pancreas, this sort of big thing, this big organ in the body, and now we're going to activate the alpha cells. Alpha cells in the islets of Langerhans. You sometimes see alpha cells like that. Sort of a little fish, but more like an egg. These alpha cells are able to produce glucagon, which is a chemical that can break down glucogen. So they release that glucagon. That glucagon enters the blood supply, gets pumped over to the liver, and then the liver takes that glucagon in and starts to break down the stored glucogen in those liver cells, and releases back into the blood supply the glucose that it had previously stored. So this is glucagon released, converts glucogen, sorry. Glycogen, that's fine. So I write glucogen up here too. So that glycogen returns back to being glucose, and then that returns us back to the normal blood sugar level. There's going to be, one of the things that we can think about is with this loop, right, is that your body is always pumping that blood around and around and around. So it's not that the first time the glucoreceptors detect this low blood sugar that they just correct the problem immediately. This is going to be a continuous thing where the blood is getting pumped past that glucoreceptor. The glucoreceptor keeps sending the signal, keep breaking down that glucogen, keep breaking down that glucogen, keep breaking down that glucogen. And then eventually your blood sugar is going to be high enough that when the blood comes back up to the hypothalamus says, whoa, make some insulin. And then it comes back down. And it's going to sort of cycle like that for life. I mean, that's part of what homeostasis is. It's an always oscillating process. So it's not just that your cells don't just get satisfied at some point. They're not smart enough. It's a system of multiple pieces are working at a time. So we can kind of make a little sketch of what this might look like. I'll put it down here. So over time, what's going to happen is this is your blood sugar here. Sugar level. And this is time. And essentially, you're going to, I'm going to actually start you on the slow side. So let's just say this is you've already, well, it's just even like, this is just a regular day. Your blood sugar is going to drop as you run out of sugar. And then this is the point where you're going to get the detection for glucogen, or glucagon. So then glucagon gets released, the blood sugar starts to rise again, and in fact it's going to keep rising and rising until the hypothalamus says, whoa, insulin. It calls for insulin, and then the insulin gets released, and then that starts to slow it down, and then it's going to say, whoa, wait a second, I need some glucagon now. And this will happen forever. This is just all day long. And then every time you go to eat, you give yourself a little bump here, right? You restart this. You start a new cycle at the top of the insulin. So suppose you might see after a meal this oscillation gets a little bit narrower. So perhaps maybe a better version of this is after eating. Let's just say eating. We can kind of imagine that you have a big spike. You have a big spike, and where insulin is released. And then that insulin breaks down, you get glucagon, and then you probably get a little bit something like this. And it will take a while to before you're back at oscillating around the normal levels. But you're going to continue to oscillate. It's never going to stop oscillating. And then you're probably going to go eat again, right? And it's going to pump back up. So you got high sugar levels, you release some insulin, the blood sugar starts to drop. Your blood sugar, your hypothalamus won't stop that signal until it detects the opposite. It detects the opposite, it starts releasing glucagon. Glucagon starts to rise the blood sugar, and then your brain says, whoa, wait a second, too much blood sugar, releases some insulin. And then over time, you'll see that switching back and forth between insulin and glucagon will be slower. Less drastic, but it will still be some oscillation. That's sort of what that's one of the concepts behind homeostasis, is that our bodies are always in flux. There's always new factors coming in. You know, people are eating all day long. Okay, great. So I'm just going to point out that we've done something with like a homeostasis cycle that might, be valuable on a test or something like that. Tomorrow is going to be our frog dissection. So I'm going to just stop this. So we will talk about. I'm going to talk really briefly about the frog dissection. You're going to get some grass frogs. They're really small. They're only about this big, little bodies, little tiny bodies. Yeah, we should be able to do it in partners of 2. Please try to arrive on time if you can. 8:45 or so would be great. As we found out yesterday we did a pretty simple lab. Took the whole class though. I was actually, in my mind, I was like, oh yeah, maybe we'll do some other stuff afterwards. And it was like, no. A lab takes the whole class. So it's definitely going to take that. I'm going to pull up. I'm going to switch here. Pull up the visualizer here. Probably have to turn this on. There we go. So this is the dissection package that I'll give you tomorrow, and that is sideways. Okay. I've not used this one before. Oh, did it already. Okay, so it's the lab I might give this to you today to take away. So you're going to we're going to be using scalpels again. And we're going to be using scissors and needles. So we're going to be doing that with the frog. So the things you'll be having, you'll have some scissors. These are going to be your main tool for cutting. Scissors are just way easier to use and way safer than the scalpel. It's really easy to go too deep with a scalpel, whereas scissors, you can pretty much cut most of the stuff you need. Yeah, they are the main tool that we're going to be using. You can place the scissors into the tissue with the tips closed. You can use the shallow angle to insert into the tissue to lift them and then cut. It's really easy to control them. Yeah, they can also be used to separate tissues by inserting them into an area, then opening them up to separate them. This is referred to as a scissor technique. That's really useful in this case because you might be wanting to look into something. You can imagine that when we want to open the mouth of the frog, you could even put your scissors in and then open the scissors, and you'll actually be able to force them open like a little pair of pliers. There should be probes. These are just used to manipulate tissues and poke them around. I'll show you a quick video of how one guy uses his set, and it's pretty useful. You'll have a scalpel. This we'll rarely use. We're not going to use them for bones or cartilage. The blade detaches for changing. I have a quick changer as well, so if you have a dull blade, we can do that. But it's useful for precision cuts. We'll have some forceps or tweezers. They're great for controlling the tissues, picking up things. We're going to have a dissection tray. I'll try to make sure we always have the ones with the wax in the bottom, so they have this sort of wax in the bottom of the tray. And that's really useful because then you can stick pins in the wax. So you can see one here with the wax at the bottom. And you can stick pins in it. Also, when they get old, all we do is we just kind of scrape out the wax with like a hot knife, and you can scrape the old wax off. Like that. And the wax washes pretty well. This wax is pretty waxy. And then you have pins. We might use the pins. They're fun, but they also can be tricky to get them to stick and things. They're used a lot in dissections. So this is the lab. We're going to go through the digestive system. So we're going to cover the esophagus, the gallbladder, the liver, the heart and lungs, alimentary canal or the digestive tract, the stomach, the pancreas, the small intestine, and the large intestine. And then we have a couple of questions at the end, which I didn't realize got really crammed up into one section. They were supposed to be all spread out. Don't know how that happened. Here's an example of what the frog looks like when you open him up. So you can see here they've used the pins to hold the skin back, and we'll try to do that as well. You can also use the pins in the arms and legs to hold them in place. So you can see that it's a little bit different from humans for sure. They have, for example, they have a single sort of organ that has both their digestive, urinary tract and things, and also their reproductive organs. They're all part of like one structure. So we can see that, but they do have a very large liver. They've got a pair of lungs. They do have a stomach that we'll be able to find, and a pancreas. They also have a spleen, and there's the bladder here, large intestine, exit canal there, the cloaca. They have arteries and all those sorts of things. They're pretty fun to look at, and talk about them a little bit more tomorrow. Okay, I'm gonna pull up. Does anybody have any questions about this dissection? Does anybody have concerns? I do not have any rubber models. I know that there's, if you're concerned about the poor frogs, I'm sorry. These frogs have probably been dead for a really long time, so this is an old bucket. So I didn't go and kill some new frogs. We had someone in our ed class who came from, they were from Kenora. And in Kenora, they were doing cats, and I don't know, that feels real sad. But she said in high school they did cats. They had cat dissections, and I thought, whoa, cats, eh? That seems like a little too much. But we will also, when we come back from spring break, we'll be looking at probably May or so. We'll be doing lungs and heart we'll do a pig lung and heart dissection. And let me see if I can find my video here. Digestion. So I added to the digestion playlist, which I believe you have. There is a copy of this video on there.
The surfaces, so we've got the dorsal surface here.
One thing I really like about this video is this guy works with a lot of confidence, and he really gives you an idea of how an anatomist can break something down. So he has a lot of he just moves very smoothly with his probe, he is one with that probe. So there's little
membranes right here. It's called the nictitating membrane.
Shows you the membrane.
Goggles, so when they swim, they can pull these up over the top of their eyes. And they have a tympanic membrane, or tympanum. It's like their eardrum.
Depending if you have a very large tympanic membrane here compared to the eye, then it's probably a male. And if it's smaller, then it's a female. So that's one of the first things we can check out.
And then inside of the mouth, they got the coolest mouths here. You'll love this. They have little bumps right under here. We call it the Vollmerian teeth, these little bumps. I know it's probably hard to see, but right here are the Vollmerian teeth. And on either side of it, there's these internal nares, these little openings. So internal nares, so I'm putting my probe in, and then Vollmerian teeth. And I'm pulling on the tongue and the lower jaw. That's the mandible. Here's the maxilla. You're familiar with that term. You gotta check out how this tongue works.
So this is a guy who teaches an anatomy course, so he keeps telling me stuff that I'm supposed to be familiar with, and I'm like, I don't know that one.
Like this.
But I do like this part with the tongue.
So that it's actually connected in the front. So it flips it out and grabs the prey, and then forces it back in to its esophagus. So it's connected in the front. So it flips out, grabs something, forces it down its esophagus and into its stomach. So a very effective way. Oh, here's the external nares. Here, one right there. When we look at the legs, boy, I tell you, these things have some serious muscles. And to really get a good look at the muscles, we've got to take off the skin. So we're going to cut right here. And these scissors are just not made for big hands, but we're going to cut around the skin here. And then we're just going to pull off the skin. Kind of like a sock. Just right off the legs. See, that comes right off there.
Anybody into frog legs?
And that will expose the flexor and the extensor muscles.
They don't taste like much.
And we'll use the same terms that that we use for our muscles. Okay?
So we got a chicken flavor.
So let's take a look at this joint. So we're going to call this like a knee joint. So when it contracts, when this muscle right here, like the hamstring, when it contracts.
Okay. So I really like this video. I recommend that you watch it. On Thursday, I have this. I'm not sure if I should give it to you now. I think it will take you more than Thursday to do. Okay, so what I'd like to do is to go through this on Thursday with you. This is sort of my first draft of the test. And I won't use this one, of course, but as you saw sort of in the last test that we did, I did use some of the questions, I played around, I moved a couple things around. So this is sort of a first draft of ideas and things that I want to put on the test, or areas that I'd like to test you on. So I called it a review, and we'll go through this on Thursdays, in Thursday's class before our test on Friday. So if you can have this done for Thursday, that'd be awesome. If not, that's okay, but because you can fill it in on Thursday as we go. But of course, it will help you prepare for the test on Friday if you do it earlier. Yeah, I'm just going to do a quick attendance, and you are free to go otherwise. As I mentioned at the beginning of class, if you were away yesterday for the lab, I did post the results of one of our teams on the Google Classroom. You're more than welcome to attempt the lab yourself. At the same time, I don't really expect you to complete it. If it is an online lab, you just complete the online form and then press submit when you're done. If you do it, you'll probably get a pretty decent mark on it because I'm pretty forgiving on those, or not forgiving is the wrong word, but I'm generous on labs because they're experience-based. It's more about getting you in here and doing something, and I'm having trouble double thinking, that's all. Okay, and okay, oh, that's pretty good. Okay. But feel free to do the lab if you can, if you want. If you don't do the lab, that's okay. I won't count it towards your mark or against your mark. I will count it towards your mark if you do it. I won't count it against your mark if you don't. The nutrition lab, though, I do believe, or the nutrition sort of activity, I think that one is completely doable by yourself. So please do that one. That's on the website as well. Okay. All right. Take care, everybody. Let's cut something up tomorrow. Woo! It's the whole point of coming to a biology class. What do you think about tomorrow? Are you going to come?
Yeah, no, I had the flu last week.
Yeah, I was just wondering about the smell and like the pregnancy.
I'm going to bring a mask.
Sure. Yeah, that sounds good then. I smelled them. They're not like the worst. They're not in like.
It's not like the.
They haven't gotten rid. They've gotten rid of all the like, whatever you call it, the stuff that they don't. Formaldehyde. They've gotten rid of all those, so these ones don't smell as bad. At least not in my opinion. But
Okay.
you might have super pregnancy smell.
Oh yeah, definitely.
Yeah. And my wife did
I'm
too.
going to bring a mask.
Okay.
I had the flu last week and I broke my phone. I'm going to have to wear it again.
Okay, but you've been keeping up on. You're okay for the digestion stuff.
Yeah.
I think you're doing fine. Do you have any assignments for me? Have you given me this and
Yeah, that's what I did.
this one, the coloring? No. Okay, that might be the one that you missed last time. You don't have to staple them together. Just right now. You have this one?
No, I don't think so.